Okay, so Appendix B was economic decision analysis about the upgrade and repair decisions for levees in the Delta. So that's what I'm going to be presenting, but kind of before I go forward with that, Jay briefly mentioned kind of some of our assumptions about the realities that the Delta is facing right now, the pressures that it's under, and what that kind of means for the Delta and its levees as we move forward into the future. I want to sort of lay that base work and make sure that everybody understands kind of the assumptions that we were operating under with regards to those factors. So this will most likely be fairly familiar for most of you here, but I am going to go over each of these briefly. There are 4 physical drivers that are starting to move the Delta towards this new reality. Those are sea level rise, subsidence, changing inflows, and seismic activity. Sea level rise and subsidence are just acting in concert to increase the amount of water pressure that's acting externally upon the levees, just by literally increasing the amount of surface area on the outside of those levees that the water is pushing upon. And what this chart shows you are some expected below sea level mean elevations for a few of the islands that we were looking at into the future. So that purple line are elevations in the year 2100 for a few of those islands. So you can see that some of them are going to be, or if not, are already fairly deeply subsided, and then sea level rise has been taken into account for this graphic as well. Changing inflows, we've already started to see this pattern, and the prediction is that it will continue, and that is with climate change, we're going to see more precipitation falling as rain rather than snow in the winter months. And what that means for us is an increased likelihood of flooding during those winter months. And so that also acts to increase pressure upon the levees. And lastly, we have this seismic risk, this earthquake risk for those levees and their foundations. USGS has assigned an over 60% chance that we experience a rather significant earthquake in the region within the next 30 years. And so as a part of the Delta Vision Task Force, the Delta Risk Management Strategy Report was written, and they tried to assess the risk that is acting upon each of the individual levees for those islands. And we ended up using a lot of those figures in our analysis that we performed. And so this was derived from those numbers. And we looked at a subset of 34 islands. So what this graph is showing you is for that subset, kind of a best case, medium, and worst case scenario in terms of risks to those levees. And this is based just upon the flood and seismic risk, I should say. So with the red line there, you have the island that had the highest probability of failure out of the 34 that we looked at. The yellow line is the island that had the median probability of failure. And the blue line is the island that had the lowest probability of failure. Again, this is from those DRMS DREAMS numbers. So you can see that even with the median island there, that yellow line, we're fairly certain that within the next 100 years, we're going to see a breach at some point in time. So there's a fairly high likelihood that within that period of time, we're going to have to be dealing with what to do when that island fails. So all of those factors together physically mean that the state is facing this sort of new reality. It's not actually new. Islands have failed in the past, but a reality that the amount of those failures is likely to increase. And what do we want to do about that? How do we want to deal with that? And on top of those physical realities, you have this financial reality where there's obviously a limited amount of funding, both private and public. There's a lot of competing interests in the Delta. A lot of people depend on the Delta in one way, shape, or form. And so priorities are going to have to be set as we move into the future. So that kind of lays that baseline. I'm going to get now a little bit more into the analysis that we did, the economic analysis that we did about levee sustainability in the Delta. So the question, one of the questions that's out there then that we wanted to ask was, how should the state optimally prioritize levee upgrade and repair efforts in the Delta? A couple things I want to point out about the way we asked this question. First off, we looked at 34 agricultural and subsided islands. So that's important. We didn't want to look at urban islands. We felt that they kind of warranted a separate analysis. And also we looked at islands that were already slightly subsided, if not significantly subsided, so that we took kind of a more at-risk subset of islands, and they were all agricultural. Second thing I kind of want to point out is that this is actually 2 questions. So you're asking, what is the optimal strategy in terms of upgrades? And then secondly, in the future, if an island fails, what's the optimal strategy then? Do you repair it or not repair it? And finally, this question has been asked in the past before, but the Delta has largely been addressed as sort of a homogeneous place in the past. So people have said, you know, does it make sense to upgrade levees in the Delta on the whole to a particular standard? What we did is we asked instead, does it make sense for each individual island that we looked at to upgrade it, and then in the future whether or not to repair it? So approaching the system as a heterogeneous kind of island by island strategy is a little bit different than what's been done in the past and the way the question's been asked. Uh-oh, we're missing a table. So I will, this is one of the translations from Mac to PC issues that I was worried about, but I'll try and articulate it rather than showing it to you guys. So we wanted to set up, to simplify the problem, we wanted to identify 6 possible strategies that the state has in front of it to choose from for any individual island. There was a table over here that had those on it before. But what those strategies were is we thought, okay, so for the current decision, the state is trying to decide what level upgrade to perform on these islands. Does it make sense to upgrade it at all? So one of your strategies could be not to upgrade that island. The second strategy would be to upgrade the island to PL 8499 standards. And the third one that we decided to look at was to upgrade islands to PL 8499 standards plus an additional foot for sea level rise to mitigate for sea level rise. And then with each of those 3 current upgrade strategies, you have an accompanying decision in the future of whether or not to repair that island when it fails. So that gives you 6 possible strategies, and you'll actually see that in a decision tree that I have later on. So if that doesn't stick with you without the visual, you'll see it again. And just kind of an aside here to make sure everybody's on the same page with me on PL 8499 standards. We'll be mentioning those a lot. So those are standards that were set by the U.S. Army Corps of Engineers in 1999. And they just set a set of physical requirements for a levee, you know, the height that it has to be above water, the width on the top of it, the slope on the land and water side. And if a reclamation district or private landowners have gotten their levees up to that standard, then they are then eligible for a combination of state and federal funding should a breach occur on their island. So because of that, a lot of reclamation funding has been going towards doing these PL 8499 upgrades. So that's what we chose to address in our decision analysis, whether or not that makes sense. And another thing I should say is also the fact that the question hasn't been asked before for individual islands. State policy in terms of giving money towards landowner and reclamation districts has also sort of addressed levees as a whole. So each landowner reclamation districts get the same percentage of their requested funding as the next landowner. So again, there hasn't really been this looking at individual islands and setting priorities yet. So how did we take those 6 strategies that I've identified and try and decide between them which one is optimal? Well, we use something called decision analysis, and this is a very similar method to what is used by the U.S. Army Corps of Engineers when they're trying to decide between various flood management projects. And what it is it's just a way to look between different options and try and decide which one is optimal when you have uncertainty about the outcome of each of those options. So the way that we structure this, and you've already seen this a little bit because Jay kind of talked about it briefly, is in a decision tree. And so this is just kind of to show the logical chronological structure of this method, of this way of thinking. And so on your guys' left here, we're standing on this current levee, and you can see that we have 3 branches, 3 possible paths to take currently. And those are our 3 upgrade strategies. We can not upgrade, we can upgrade to PL 8499, or we can upgrade to that PL 8499 plus an additional foot for sea level rise. So that's currently. Then at some point in the future, that island is going to fail. We're not sure when. So that's where that uncertainty comes in, and that's what those circles represent. Those are our nodes of uncertainty. At some point it will fail. We don't know what year. And of course, with different levels of upgrade, you're going to have different probabilities of failure. And then when you move into the future, after that island has failed or breached, then you have the decision of whether or not to repair it. So what you're left there on the very right-hand side of this tree are your 6 present cost calculations for your 6 different strategies. Which is all fine and good, and it makes a lot of sense, but the problem is that you're trying to decide between 3 different strategies right now, which of those upgrades makes sense to perform on the island or on the levees. And so with decision analysis, what you often have to do is look to the point furthest in the future and try and eliminate some of those future options. Say, what would I do in the future if this island were to breach? Would I repair it or not? And then it'll make more sense to weight those costs back to the present and try and decide between your upgrade strategies. So we'll do that first. We'll look at our future decision of whether or not to repair an island. So if you're standing on an island and it's breaching, you're trying to decide whether or not it makes sense economically to repair it, you're going to be comparing 2 numbers. The first of those numbers is the value or cost, it can be looked at either way, of performing the repairs on that island. The other number that you're comparing that against is the value or cost of not repairing the island. So what you see on this slide behind me here is the first of those two numbers, which is the value or cost of repairing the island. So incorporated in that, you have the cost of actual physical labor and materials and things like that that you need in order to perform the repairs. You're losing a year of profits because you're not able to farm on the island for that year. Again, I should emphasize this is agricultural island. You're also losing repair costs in the future because you're not actually addressing the foundation of that levee, and the repair that you're performing is on a very small portion of a very long levee. So you are likely to have that failure occur again, and you have to incorporate that somehow. And then subtracted from all of that is the property value of the island because you're maintaining that and you're getting to use the island into the future. And you can see kind of how we mathematically represented that down below. So you have that number, and then you want to compare that number against the cost of not repairing an island. So the cost that you're facing if you don't repair that island, and we saw it as being two costs. And the first of those is that you might have infrastructure on the island that you'll have to replace. So roads, rails, things like that, railways, I should say. And then the other one is you're now exposing these surrounding islands to an open body of water that they weren't previously exposed to. So that exposes them to wind and wave action and things like that, and so you have to do some kind of reinforcement to those surrounding levees to account for this new pressure that they might face. So we try to incorporate both of those costs as well. And now we are able to decide, okay, in the future, what makes more sense? Do we repair the island or do we not repair the island? And we're going to take the example here that we've decided that we would repair the island, and so that's why I've circled those pink boxes. We don't have to worry about the blue boxes at all anymore. We know that we wouldn't not repair it. We're going to repair it. So now it makes more sense to try and evaluate between our three upgrade strategies there. And this is where probabilities of failure become very important, because obviously you're not going to perform an upgrade on an island if you don't think that that upgrade is going to protect the island somehow or make that levee less likely to fail. So we needed a way mathematically to make sure that, you know, the cost of upgrade could be offset by a decrease in that probability of failure, that if that upgrade is significantly effective, then that makes it worthwhile. So how do we do that? This is just to emphasize the probabilities of failure. If our island is repaired in the future, then all three upgrade strategies are evaluated using this same equation. And you can see in this equation how probabilities of failure work to offset the cost of those upgrades. So for instance, if you upgrade it to PL 8499, there'd be a cost for doing that, for performing that upgrade. However, if it was the ideal upgrade and it reduced the likelihood that that island was going to fail in the future to 0, then you would completely eliminate that middle cost term. And so they're able to work and offset each other in that way. And then again, if you're repairing an island, you're maintaining that property value of the island into the future. So that was kind of a walkthrough of how the model functions and how the equation functions. I wanted here to kind of put up a review of some of the major inputs into our model. These are the big players. These are the variables that matter the most in terms of what changes the results. And so this is just sort of a reminder of that and a review of that. And what we did is we gathered data on all of these variables for the 34 islands that we were interested in. We put all of that data into the model that I just kind of walked us through. And then that model gave us results of how many islands were repaired, how many weren't, how many were upgraded, and so on. So what do those results look like with our first cut? This map here represents the repair decision. It doesn't represent the upgrade decision. And I'll explain the colors. The blue islands were the ones that were not repaired by the model. The gray islands are the ones that were. The yellow islands we assigned to an indeterminate category because they fell fairly close on either side of the repair decision, and so we just decided we couldn't say for sure with those. And then we redded out some islands because we knew that they were important for water export quality, and that if you're still counting on the delta to export your water, you're going to need to repair those islands. They'll be important for that. And then finally, the green islands down there are urban islands, and again, we didn't look at those, so we wanted to point those out and keep them separate. A couple striking things about the results. 10 to 19 islands were not economically worth repairing after a flood. And also you'll see that that's kind of a geographically consistent result. We didn't do any spatial analysis or anything like that as a part of this. But it just turns out that mostly I think because of subsidence and the fact that some of those islands in that area are more at risk, possibly because of low value agriculture, but I'm not sure on that. There is a geographic consistency to where those do not repair choices are made. And that may or may not have important implications for policy moving into the future. It may make things easier. The other result was that none of the islands that we looked at were upgraded economically. And that seems like a very surprising result. I was surprised initially when I saw that. But the reason for that is that we went out and talked to a lot of engineers and people familiar with levees in the Delta and asked them, what kind of percentage decrease in the likelihood of failure do you think you obtain from performing a PL 8499 upgrade? And most of them said somewhere around 10% decrease in likelihood of failure. That's it. And the reason for that is that you're not addressing the foundations of the levee. A lot of the risk inherent is due to seismic activity and earthquakes. And so you're not really dealing with that risk by performing a PL 8499 upgrade. So that's the reason for that result. However, we recognize that our inputs may not have all been correct. And there's a lot of interesting kind of follow-up questions that come from this initial analysis. And we wanted to see what would happen if we changed a lot of those inputs. So one of the questions that you could ask then is, what if we were wrong about the upgrades? And first of all, they might have been a lot cheaper than we had thought, and they might be a lot more effective. Another question that we wanted to ask is, what if reinforcements to surrounding islands in the case of allowing another island to flood actually cost a lot more than we thought they would? And third, what if property values were increased? So maybe we underestimated the property values of some of those islands. What happens to our model results if we, say, double those? So these are the results of the sensitivity analysis. This is the first question that I asked about upgrades being cheaper and possibly more effective. So this is perturbing two variables in the model here. Along the bottom there, we've made the upgrades more effective by decreasing the likelihood of failure by 10% increments there. So basically on the right-hand side where you see 90%, that's your most effective upgrade. That means that with a PL 8499 upgrade, you have a 90% decrease in the likelihood that that island fails. And once we did that to all 34 of the islands, they were all within FEMA floodplain standards. So that was a very significant amount of a decrease in likelihood of failure. And then those three different colored lines represent different economic scenarios, so different costs for upgrades. The top line in the red there is the cheapest one, or the cheapest estimate that we had heard, which was $850,000 a mile. And our bottom one was kind of the most expensive we thought it could be, which was about $4 million a mile. And the middle line is what we actually used for those first results that you guys saw, which was $2,800,000 a mile. So basically that red dot up there on the very right-hand side of the graph towards the corner is your kind of best case scenario for the sensitivity analysis. It's the cheapest upgrade. That's also the most effective. And what you see is that there is a significant change in our results. So a lot of islands then become upgraded. It makes economic sense now to upgrade 25 of those islands. But what's also important here is that it still does not make economic sense to upgrade 9 of them. And so this is kind of a theme that'll be reiterated through some other sensitivity analyses that I'll show you guys, which is just that it makes sense, it seems, to look at each of these islands individually and to stop approaching things and the Delta as one homogeneous place and to sort of approach it more as a diverse place. So the second question I don't have a graph for because it was a kind of a boring sensitivity analysis. We increased those costs of reinforcing downwind islands and not very much happened. So we quadrupled those costs and eventually, finally, 2 islands switched from the do not repair to the repair category. But really we had to perturb these numbers quite a bit to get anything to happen. So that's why there's no visual there. Finally, the question about property values. We doubled the property values for the islands. So you can see that percent increases in property value is running along the x-axis down there. By the time you get to the right-hand side, you have a 100% increase in property value. So again, that's doubling the island of the value of the island. And along the y-axis, that's the number of islands that were then repaired. And so again, you do see a change. So 6 islands switch from the do not repair to the repair category when we do this. However, again, you still have a significant number, I believe 13, that are still not repaired. And this is a little bit different from the map you saw because we don't have an indeterminate category incorporated here. So if people are kind of wondering about the difference in those numbers, that's why. But again, that same theme where it makes sense to address these islands individually. So that brings me then to the conclusions that we could draw from this. And the first of those is that the current delta landscape seems uneconomical from a statewide perspective. The second, selective upgrades and repairs are more economical and preserve finances for other purposes. So again, there's a lot of competing public interest in the delta, and maybe it makes more sense to use some of that money for other things. Physical and economic drivers will return portions of the delta to open water. We feel that in light of the physical drivers I went over in the beginning of this talk, along with those financial realities and restrictions and what makes sense financially in terms of upgrades and repairs, that portions of the delta are going to return to open water. Those are the conclusions that we could draw, but the model and the analysis that we did also kind of begs some new questions, and some of these we're working on now and into the future. And the first of those is to explore kind of other reasons to assign higher property value to islands. So we didn't really look at cultural reasons or terrestrial habitat, some things like that. On the other hand, there might be reasons to assign value to open water for kind of similar purposes. Secondly, we wanted to include changing risk due to sea level rise and subsidence. So the probabilities of failure that we used from DREAMS, those were static. They only changed based on upgrade level. But what we didn't do was make those islands more at risk as sea levels rose into the future. So that'd be another thing to kind of look at and explore. Third, like I mentioned when I was talking about that first moving forward step there, we want to explore maybe there's some value to flooded islands. We really don't know exactly what different areas of open water might do for habitat and recreational opportunities and things like that. And finally, this is kind of the big one out there, are what are the true sort of water quality and hydrodynamic effects of open bodies of water? What does it mean in terms of wind and wave action? What are some of the possibilities in terms of seepage and things like that? Those all need to be kind of explored in further detail if this reality exists that a lot of these islands are going to start moving in that direction. So this was supposed to be, and do we have any success on the animation? Okay. So with that then, since I don't have the animation to show you guys.
Do you want me to, I mean, I've got them on another laptop. Do it.
Sure. Yeah.
I believe we have,
Well,
so that means we have to plug it in. That's okay. Let's do it. This is not a map. Let's do it. Okay. So this is the.
Well, I can take questions then maybe as people are fiddling with the animation.
It might not play through. That was the issue before.
Well, it's okay. We've got time. Let's do it. Yeah, we can do that. No problem.
Anybody have any
Questions
questions for
for
me
Robyn?
as this is happening?
Go ahead.
So it wasn't really clear to me how you took into account the effects on exports. You just had the one map that you showed slashed lines, but
Right.
to me that's pretty important, how
Right.
you came up with which islands had the slashed lines, and were those some of the 34 or not, and
So I've been giving permission to deflect some questions, and I'm going to do that now. So the deflection goes to Bill Fleener because he actually did the analysis on which islands were important for water quality exports in different regions of the Delta. So I would ask him that.
oh, you'll answer in the next talk, not now. Oh, okay. All right.
Interdisciplinary.
But well, what were those include? I don't think this is this on? Oh, it is.
Yeah, they are.
Were those part of your 34 or
No.
not?
No,
Okay.
that wasn't a part of the analysis.
Okay. So those were excluded up front.
Oh, those islands that were redded out, some of them were a part of the 34, which is why, on the map we just have to red them out because some of them were blue.
Okay. Can I ask another question? Then
Yeah.
ask someone else. Sure, go ahead. What are your in terms of what do you think was driving, if anything, the outcome in terms of you had that one area, you had kind of that common area of the blue. Was it the crop value or was it the cost of what was really driving the groupings?
Oh, I think that two factors were sort of the largest, and crop value certainly, so property value. was a really big driver, and the other one was the risk that those islands were facing. And I think those islands are more subsided than most of the other ones, and so their levees are more at risk, which means you have a higher, failures occur more often, which makes them more expensive to maintain and keep repairing, and so on and so forth.
They're also more expensive to repair, more deeply subsided
Right.
islands. The ones that, the islands that were most deeply subsided tended to have the less amounts of infrastructure on them, although there are certainly some exceptions to that. They have tend to have lower value crops. They tend to be more susceptible to failure, and those things all seem to correlate in the central and western delta, well, particularly the central delta. That's, as you'll see here in this animation.
Okay, so
This is the no repair.
oh, okay, so we have two animations. This is the scarier looking one, which is taking those dreams probabilities of failure and just figuring out what the recurrence interval for failure is from those numbers, and failing islands at the year that they would if dreams had gotten those numbers exactly correct. So that's what this animation shows you first. So I'll let it run, and if people want to ask me a question while it's running, that's fine too. So you can see that pretty quickly there, this kind of goes to show that those islands are thought to be at fairly significant risk for failure by how quickly most of them see a breach and then flood. Can we move to the next one?
Sure.
So to compare to that first animation, we also have an animation for the analysis that we performed in terms of the economic sustainability of those levees. Which islands would you repair? So it takes those same dreams probabilities of failure, floods those islands at the recurrence interval, but then if the model had repaired those islands, goes ahead and turns them back to white after a year. So this one should look a little bit different, with some areas remaining blue, others being repaired. And I should say also that, again, the indeterminate category is not figured in here. So some of the islands that weren't blue on the first map might end up being blue on this one. Okay, so any other questions?
Yes, please. So I guess this harkens back to the notion that Jay introduced earlier, was that, at any point in any of these analyses, there's a whole list of, well, you didn't consider this and you didn't consider that, which this necessarily immediately brings to my mind, particularly when you got some guy who's standing on a piece of ground that floods and he says, no, I'll fix it, and go away. So, thinking about what we're going to hopefully get to tomorrow, where do you go in the decision analysis to get you out of an argument that's, just based in, well, I would fix it, whether you think I would or not, and, how do you make these things real? And, I mean, we're sort of caught in this, well, that's really interesting information, and if all other things being equal, which they never are, this would make sense. Can you make these numbers, I guess, more real for me? Do you have I know that's a difficult question, but I think you've piqued our attention, and now we want to get into the details, I think.
I think what this tells you is what makes economic sense, and then whether or not that's a piece of a larger conversation. Obviously, there's other things that are taken into account when you are deciding what to do, and whether or not the state takes that into account. I'm not the person that's speaking about sort of how to move forward with that, but I think that this is a rather kind of simple and clear way of at least deciding whether or not it makes economic sense. So you can take that piece of knowledge, and then that becomes part of your conversation that's a little bit broader. Does that answer that question?
Begins to, sure.
I think that she has about right, that essentially this is looking at it as a business decision. If you own an island and you raise crops on it, so you're making a profit off of that island, would you fix that island if it broke? And for many of these islands, you wouldn't. So sure, if you want to go ahead and fix that island, go right ahead, but eventually you're going to go broke doing it. And it'll be like Frank's Tract, unless you have the state aid come in.
Right.
And then the question is, does the state have a compelling reason to come in and subsidize those islands? as you'll see some the results in Bill Fleener's talk after lunch, the state doesn't have a compelling water supply interest necessarily in all of those islands, maybe only in the western ones until there's an alternative.
I want to remind you that we already have a policy in place. The state already has this policy. It just they haven't acted on it. So after the Jones Tract failure, Lester Snow announced the DWR's policy was that they would participate in a flood fight, and they would that's where they would help. But after the breach is taking place and the flood fight is over, a decision to repair will be based upon a compelling state interest. So in fact, this is a test of Lester's policy. That's what that is. That's a compelling state interest on an economic analysis. Now, it might be that if Staten Island floods, let's talk about direct examples, because it's really better to actually talk about specific islands so we can get to your question. So Staten Island floods, that's a big island, and it landed in Robyn's indeterminate category. It's a big island, long levee, deeply subsided. It's more than 20 feet at its southern end. Very expensive to take care of it. But on the other hand, 14,000 sandhill cranes roost there every winter. So it might be, there would be a compelling reason to go ahead and restore that island. We didn't figure that in because we don't know how yet to figure that in. I know that Dreams tackled some of this by having the in-delta interests kind of rank with, like 1 to 5 kind of values, and somehow mashed it all together into whether to repair or upgrade islands. I still don't quite understand how that was done. But we haven't done that part of it here. It's just economics, which is,
But even on that case for the sandhill cranes, you'd have to, from the state's perspective, you'd want to think about it. Gosh, is it better sandhill crane habitat for us to spend this millions of dollars upgrading that island or rebuilding that island and then have a probability of still failing, or are we better off taking those millions of dollars and buying up another piece of land and dedicating it, maybe land that's above sea level, and dedicating that to sandhill crane habitat?
I want to add something else since we have time for conversation about this. The other interesting thing that you can take out of this, when you do this is just, bare bones economics and how you would prioritize investments that you make. Let's take one that Cliff might be asked to help on, and that would be subsidence reversal, for example. Where are we going to put our carbon farms, for example, carbon sequestration farms? Well, how do we prioritize those decisions? Well, this is actually kind of an interesting first cut. I think one of the things that you might worry about if you were starting to say, like, I want DWR to make a carbon sequestration farm on, let's pick an island. Twitchell comes to mind. I see Dave Mraz is here. Twitchell Island comes to mind. Well, what is the probability? That is, what is the probability that you'll actually get to sequester very much carbon on that island before it fails? And then once it fails, would you fix it? And this is sort of a systematic way to step through those kinds of questions. And again, ignores all the other values, but I think Robyn did a really good job of getting at that sort of most basic and fundamental question.
Something too is that the spreadsheet for the model is available online. So you could actually go in, and if you had different ideas for how you might value some of those other factors, you could play with the inputs to the model and sort of see how the results might change. So that's available to everybody on PPIC's website.
As a general policy, we've tried to make everything that we can available in a way that can be used where that's possible.
All the source data and everything is on there as well.
I have a quick question. It looked from your map, and I'm getting back to the water quality thing, so then maybe this is something you get to later on, that the scope of what you analyzed was kind of restricted to the delta. Will you also be looking, or have you looked at the effect on water quality of restoring islands in Sassoon Marsh and further west from the delta? Another question for later?
We didn't specifically address that in this piece of work, but it is certainly something of interest. I mean, there's been a couple of pieces of work done in the past, one because a levee did fail in Sassoon Marsh. And so a couple of things have been examined about opening up parts of the marsh. And interestingly enough, it changes kind of the phase through the delta of the tides. So it's something that's certainly going to have to be taken into consideration, and something, as we discussed, sea level rise is likely going to occur anyway. So yeah, we're gearing up to examine those questions.
It just seems kind of odd that you have these 2 or 3 Western Delta islands, and these are the ones that are water quality importance. It's kind of like a hinge, and it's, whatever happens on either side, those are really the important ones. But whatever happens on either side, maybe it's not so important, but I think it probably is.
Well, there's certainly some importance as to what happens on either side, but not the direct importance of those ones that are actually controlling the flow.
My recollection is that there have been some studies done, I think, with Liberty Island. Maybe, Bill, you can correct me if I'm wrong, where they found that the failure of Liberty Island actually dampened some of the tidal amplitude, which should actually dampen some of the mixing, which might improve water quality. So I think there are some, depending upon the location, where they are with regard to the tidal harmonics, you might find some failed islands that actually improve water quality and others that are bad. So this, I think, illustrates some of the very different kind of delta that we're moving into and how we're going to have to do a very different kind of analysis on it than what we've done in the past.
This is Dave Mraz with Water Resources. I've got a question or two. You used the results from DREAMS Phase 1, and that study was based on business as usual. And business as usual is putting just a minimum amount of funding into the Delta levee system to keep it viable. I think we've already made the change to invest more in our levee system. Witness the money that's coming out of Proposition 84 and 1E. How would that increased level of funding on the levees factor into your judgment about the economics of retaining or losing islands?
I think that, well, let's see, the easiest way to talk about that, I think, is to talk about how probability of failure kind of plays into the model in terms of different steps in the model, different decisions. So you have a base level, and that's what we use DREAMS from. And then we took that base level probability of failure with your current levees and sought out how upgrades might change that probability of failure. And that difference between those two probabilities of failure, which for our first run was only 10%, is what really sort of drives that upgrade decision. Because if the difference isn't great enough, then it doesn't make sense to spend the money. So, so the fact that, so you could say then, okay, some money's already been spent, so maybe those initial probabilities of failure are a little bit too high. Actually, if you decrease those initial probabilities of failure, you're kind of biasing the model away from upgrades making sense, because your 10% decrease now from that initial probability of failure is going to be less than it is if you have a higher initial. Does that make sense? Probability of failure. So I don't know if that answers your question. Is there, Jeff has something?
Actually, Dave makes a really good point that we haven't really discussed. And it's an oblique point. Sorry. It's an oblique point, but it really does matter who pays for this. So whether if you were to, so our analysis is the 40,000-foot statewide, broad statewide interest. But if you're a landowner and you own or you own a piece of a land, or you own a whole levee, a whole island, it's going to make a big difference who pays for this. So if the state comes in and gives $1.4 billion, which is a number that's been kicked around out of 1E and 84 as a combination, I don't know what the total amount will be invested in, but yeah, I wish you would. Yeah, sure. I guess you do. Well, let's just say, for example, say $1 billion was going to be put into Delta levees. If you own Jones Tract, which you're currently suing the state over the repair of it after that flood, that's going to really change your economic equation. But we didn't take it from that point of view. We took it from the statewide point of view. But that's a really important point.
I was going to say something about Jones Tract, but I think I'll bypass on that. Yeah. I apologize for not being here for the early part of your presentation, so I don't know whether you considered the assets of statewide significance, the highways that go across, the railways, the
We did.
pipelines. in
Yeah,
your analysis?
we got the data on that from a combination of GIS data that gave us the length of the road and rail that were crossing the islands, and we also got asset numbers from, again, Dreams. So we counted both of those. And we had a multiplier for, how much it would cost to replace a certain length of road or rail. And again, that can be found online. I actually have it here if you want to look at it later.
The other question, I guess, that I have is, can we rerun the analysis after we decide what Phase 2 is going to bring to us and use it in some fashion to help us make those decisions?
Yeah, again, the spreadsheet is there and the model is there, and so you can change all of the inputs. Any of those inputs that I went over, you could go in and sort of re-put those in and see how the results change. I think that's one of the most valuable things about it. Yeah.
I've got two questions, one I think which is a hydrodynamics type question, and one which is going to be more of a engineering type question. So I'll start with the hydrodynamics question. I think it's something, Jay, you already alluded to. As you change the geometry of the system by flooding 1, 2, 5, 10 of these islands, the energy that's going to be dissipated in that tidal prism is going to change, and the magnitude and amplitude of the tidal fluctuation and stress on levees is going to change. Did you factor that into the analysis as you might change this?
In minute detail? No, not at all.
No, did you try at all to reduce the probability with time?
I don't think we have. I don't think that capability exists in California yet.
The modeling side.
Yeah.
That's one of the things we want to pursue in the future is an ability to do that kind of work.
Because I think the spatial component becomes pretty critical then, is which islands, where.
Yeah.
Absolutely. And we're kind of in the dark about that now.
Yeah. And then the second question had to do with your factor of 5 in terms of your cost for your estimate for levee upgrades from 800,000 up to about 4 million a mile. Could you give me a little more detail on how those numbers were generated?
Gosh, I wish I had this. So the 850,000 was from a contractor that works on upgrades in the Delta. It was just one of the lower estimates that we heard. So we went out and talked to a lot of different people that do these upgrades and got numbers from them of what they thought their costs were or what they were charging reclamation districts for those upgrades. And that was the lowest number that we saw. What was the upper? I don't remember where I think Dreams might have been the upper number. Yeah, so we basically we had a bunch of different estimates for a per mile cost for those upgrades, and we just took the highest one that we saw and the lowest one that we saw. And yeah, it is pretty incredible.
So this is contractor estimates then that you used for these numbers.
Yeah.
Well, in Dreams, there were a number of different cases considered, and I think the $4 million per mile is probably just to upgrade the levee in place for PL 8499 plus a little. There was numbers as high as $20 million per mile if you wanted to do a full seismic repair. So we're really talking here in the $800,000 to $4 million range of doing repairs that resist static loading only.
Right.
And the other question that interested me, that gets more of an engineering type of question, is that there have been numerous failures, and I'm sure those failures have been analyzed and assessed in some detail. How many of those failures have been from foundational failure versus overtopping kinds of problems?
Who knows? The record of failures goes back 100 years, and just in my short tenure in the Delta of about 10 years, I can say that there's quite a few foundation and embankment piping scenarios that have occurred. I can say that overtopping does occur, but generally speaking, it doesn't cause levee failure because you have people out there actively managing that. I think most of the failures in current times are from under seepage, through seepage, that sort of a thing. Beaver holes.
Thanks.
The higher the water gets, the more likely it'll fail by non-overtopping as well.
Right.
Any more questions?
I'm just wondering if you looked at, were there some islands where it was critical the value you put on the infrastructure? You know, so for example, they would have been in the do not repair category, but infrastructure put them into the other.
Yeah, I think if you look into the details, that most of the islands that were readily repaired by the model have some sort of state infrastructure running across them. So that factored in pretty heavily, I'd say.
Have the values, economic values that you used in your modeling effort changed substantively due to the economic changes in the country as a whole here in the last few months?
I do not know a good answer to that question. Maybe the economists can answer over there. But you, again, we played with those numbers a lot. We played with all the inputs quite a bit. So the result that it makes sense to look at everything individually, I think, stands sort of no matter how the economics might change.
So I had one more, if you would, if we're. So again, thinking ahead about what Jay was talking about, and certainly echoing some of the interests in all of this that the science program has in helping foster this conversation. Do you find that people respond to this kind of information with further interest and willingness to participate, or does this balkanize people and send them screaming into the woods? I mean, what are we likely to see over the next 18 months? People are going to sort of stand their ground and say, not on my dead body, or not over my dead body. Yeah. I mean, because is this helping us? Are having these conversations helping us from your perspective?
I'm going to answer part of that, having been involved in this for some years too. This is the first time this has been done in some systematic, objective fashion. And it's wrong, because Jay is our leader, and he will tell you all models are wrong and some are more useful than others. We know it's wrong, but it's useful, because what it does is Robyn really identified it. We can't treat the delta as a single homogeneous unit. We've got to do it individually. I was really surprised at the results, specifically that geographic cluster of the do not repair islands. That's significant. I think that, it might be, give or take an island here or there, you might change that geometry, but from a future ecosystem perspective and how to think about the future, it's really the first time we sort of sat down and said, it might look this way. You're going to see it again when Peter puts up his ecological dream map. Later, you'll see that part of the economic driver, which, we all focused on the 4 physical drivers of change, but the economics of this is going to be as important as anything else. So I think this is really useful. And the reaction we've been getting is very interesting. Almost no reaction. And I'm not sure what that's telling us. Do you know what I mean? We were getting lots of other people screaming at us about other things, but this map has been now reproduced. It's all over the place. Jay can chime in on this. And I'm surprised how durable it is. As probably one of our more robust results.
This study is really the main appendix for the first major conclusion out of the 2008 study, that you're going to have large quantities of open water in the delta, more than you have now. That it's going to happen. People can resist it as long as they want, but as individual landowners, you'll drive yourself out of business doing it that way, unless you get a tremendous amount of state aid. And why should the state do that? The state has, another many billion-dollar hole in the ground, just nearby that they're going to have to fill. Why would this be a good draw of that kind of resources from a state that doesn't have that kind of money? That's really an important conclusion, I think, for the strategy of how we think about the system and the future of it. It's a very difficult realization for people to accept, because for 100 years we've been denying that this would happen, even though you can go back to the early 1900s and find people writing about, gosh, these levees are lousy. We're not going to be able to keep these forever.
Well,
For
speaking
100
of which,
years, I mean, it's really remarkable. When you talk to the levee engineers, it's remarkable how well they do. I mean, it's a tribute to the success of individuals and reclamation district that this system has gone along. But in the long run, certainly with sea level rise and continuous subsidence and earthquakes and things like that, one big shake, it's all over. You'll drive a lot of people out of business. And I think it's at the technical level, we get a lot of emails. We have a lot of conversations. Gosh, I'm really glad you did this study. It's really nice. It shows things that people really need to think about. But those are sort of private conversations they have with us. Nobody's sort of getting up in front of the microphones and saying, hey, wait a minute, the way we do BDCP and the way we're doing Delta Vision, that's just not going to work. And I think that's a problem that will take some time for people to realize.
Now, you asked a couple of questions of how is it received. I think in the Delta, that's most of my contact. They look at it and they say, well, it was a foregone conclusion that this was going to be the outcome of the study. So they're pretty much writing it off. You asked about why the state would invest funds in the Delta. Well, because the legislature told us to is one reason. But the fact is that the Delta does have a lot of benefits that it brings to the state as a whole, not the least of which is its water supply. The agriculture, the tourism, I don't know, you can go down quite a list of things. So as long as we have to continue to get those things out of the Delta, I think the state funding has to be there, because as you've already observed, without state funding, there isn't enough money in the Delta to be able to sustain what we're now getting. So the way that I tend to look at the reports is to look at and say these conclusions are based on a geologic timescale. Yeah, in 200 years we'll have much more water in the Delta than we have today. However, we have to get there. So there are things that are going on right now. They talk about isolated conveyance, and they talk about through Delta conveyance. In order to have through Delta, you have to have state funding. In order to have the isolated conveyance, you have to have state funding until the thing is through the courts and built. So from my perspective, there is no alternative at this point, no viable alternative, but to sustain the Delta until the state makes some very hard choices. So that $1.4 billion, if it should come, I think will be well used, sustaining the Delta.
For a short period of time.
For a short period of time on a geologic timescale, yes.
I want to answer this real quickly. And Dave and I have talked about this like 100,000 times, but I don't view this as geologic timescale. This is a generation. This is for what we worked out. That was 2050. My son will be looking at retirement at that age. So this is, in my view, a generation, hardly geologic timescale. Maybe Sarah Palin views it that way, but I'm not sure.
Something that also might be worth saying is that this, I mean, at least this Appendix B does not try and ascertain. Again, it didn't approach the Delta as a whole. It didn't say whether or not the state should spend money on the Delta. It looked at individual islands, and so I don't think it's necessarily asking, whether or not funding should go towards sustaining parts of the Delta.
I mean, the point has to be made, and it really, again, I have to remind you, most of the Delta in her model, we keep it. I mean, the vast majority of it, we keep it. It really is a cluster of islands, deeply subsided, low-value crops, low amounts of infrastructure. That's why I mean, this is helping in a decision. We would say, yeah, you actually prioritize these islands in this case. Those islands with high value to the state and the local economy, in that model, you fix them. It's the upgrade question, which is, I think, in many ways, much more controversial.
And I think another aspect of that is what was alluded to before. You want to do some hydrodynamic studies on what's the effect of these particular islands on the water quality in the intermediate term, short-term and intermediate term, to pull that through. It's sort of a window on this new Delta that we're moving into.
Jay, do you think that ultimately you would actually be moving towards answering the question of which islands should be flooded first, second, third?
Oh, that's a really good question. You'd have to sit back and say, well, what's the purpose of flooding some of these islands? You might have habitat reasons for flooding some of them. You might have hydrodynamic reasons in terms of changing the way the water quality works. You might have precautionary reasons to flood an island so that you have these very large, deeply subsided islands. Maybe you want to pre-flood some of them so that in the event of an earthquake, there's less of a big sucking sound that goes on. You might do it for experiments. You want to say, well, since we know a lot of these islands are going to go in the long term, maybe we want to do experiments on a few of these to see how the ecology works and how the hydrodynamics works and how the mixing works and water quality works and how the TOCs come out of the soils and all kinds of things. On a few of these in a controlled environment where we can study them to try to get out at least our minds a little bit ahead of this thing. Because these are going to be hard decisions. I think when you look at those decisions, the thing that worries me the most is our inability to make decisions. We can have all kinds of modeling studies. Those are cheap. Those are easy. We can do those in a year's time. It's just amazing how many studies you can do in a year's time if you have a will. But to make decisions on this scale is, I think, something that we haven't prepared ourselves to do. And the kinds of things of deciding, well, which islands when, that's going to require a level of decision capability that we haven't seen for a while. But I think our science work helps make it more possible, more likely that that kind of capability will evolve.
Okay.
Thank you very much, Robyn.
Thanks, Robyn.
I guess it's time for lunch. Take 2 each.